Okay, so in this particular problem, we've got the situation where, remember, one of the things we talked about yesterday was that they're the like all or nothing problems. So all four of these cards are blank. None of these cards are blank. And those are pretty straightforward because we can either find the probability of something happening 4 times and multiply it, or it can be the complement of those probabilities. Yeah, you're good to go if you're done with TAing for the day. Anyways, so the probability of the complement 4 times in a row and multiply those together. So the all or nothing are pretty straightforward problems as far as it goes. It's the at least one of problems. I don't have this going yet. Okay, so at least one, that phrase right there turns it into something you have to just kind of think through a little bit more, and hopefully, and some of you did think through it and get the correct answer here. And some of you probably thought through it, just maybe not far enough. So anyways, let's see. The probability that at least one of the 4 cards drawn is a diamond. Okay, so the only way that this doesn't happen is in the specific scenario where we get not a diamond. So I'm going to put D means getting a diamond, the complement of that. So I don't get a diamond for the first card, and I don't get a diamond for the second card, and I don't get a diamond for the third card, and I don't get a diamond for the fourth card. So if that happens, I have failed because I'm trying to get at least one diamond. So if I get no diamonds for all 4 cards, I've failed. So now kind of the way that we can think through it is, if this is the probability of failure, everything in parentheses here, this is the probability of failure, well, then the complement of that has to be the probability of success. So I'm going to take the complement of all of that. So what I'm really saying is that 1 minus the probability of failure gives me the probability of success. All right. So now we can do this. The probability of, or actually, let me write it this way. 1 minus the probability of failure every single time. I know it's kind of annoying having to write all this out again. I mean, and you don't have to show it exactly this way if this was a question on your test. So now we just need to figure out what is the probability of failure. So every single time we're starting with a fresh deck of cards, basically, and I could get any random card from the deck. So every single time I have a 1 in 4 probability of getting a diamond. So the probability of not getting a diamond is just going to be 1 minus 0.25, so 0.75. All right, so each time I draw a card, there's this 0.75 probability I don't get a diamond. All right, so now I can start plugging numbers in. So now I've got minus, and the probability of all these ands means I just take these probabilities and add them to, multiply them together. So that's going to be 0.75 times 0.75 times 0.75 times 0.75. Of course, you could just do 0.75 to the 4th power. And that's basically the calculation that we need to do. And once you do that, you should get this right here, if I did my math right. So there you go. That's kind of the approach to this problem. And just to remind you, we spent a lot of time thinking about it yesterday, but I want to remind you more that at least one phrase is going to give you a hint. It's like, don't just rush through this and go with your first thought, kind of think through what the scenario is really asking. Okay. So hopefully you're feeling good about that from yesterday. So we are going to run through most of chapter 15 today, not all. We'll save a little bit just, for whatever reason. So, but we're going to go through kind of the heaviest part of chapter 15 today. The idea is on Monday, we'll cover the rest of it and spend hopefully the bulk of the time really looking at a lot of different problems like it might appear on your test, which will be on Tuesday. So Monday is going to be finishing up chapter 15 / unit test review. So you might not leave class today feeling like you've mastered this stuff, but hopefully Monday you leave feeling like it's all coming together and clicking. All right, we're going to talk about our general, the big thing really here is the general rules, general addition and general multiplication. Okay, and we're going to start with our general addition rule. So our addition rule doesn't work for non-mutually exclusive events, and why is that? You can kind of see this diagram right here that does a good job of explaining it, but what I want you to think about is the fact, I've got some stuff here kind of explaining this, think of this as an actual geometric diagram showing the area, right? So 100% of your possibilities fall in this box. This represents some fraction of it, that's some fraction. So if I can add those two areas together, then if they are mutually exclusive, they do not intersect at all, I can just add these two areas and that combined area will be whatever fraction it is out of the 100%. Pretty straightforward if you think about it from a geometric perspective. Now, if these do overlap, when I add these two areas together, I'm double counting this area where they overlap. So that means, if I'm thinking again like a geometric problem, if I just add the area of circle A and the area of circle B, then I'm over counting the total area of the combined. So that means I can't do it that way, and I need to subtract away the overlap. Otherwise, I'm counting it twice. Okay. And hopefully just from the diagram, it's kind of making sense why that's the case. Okay. Yeah, and so these are not mutually exclusive because A and B can both be true in this area. And anytime the events are non-mutually exclusive, there will be some amount of overlap. If we were trying to draw this stuff out to scale, then of course you might have different sized circles that have some amount of overlap. But I mean, typically we don't care about drawing probabilities to scale. There is something called geometric probability, which we don't really get into, but that involves using things like that. We'll see if we ever talk about that or not. It's not really on the AP test. Okay, so here's the general addition rule. And it was already on the previous page, but this is using the actual notation. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. They're non-mutually exclusive, so it's worth pointing out right here. All right, did we talk about it? Yeah, we do talk about it later, so I'll just wait until then. Okay, so before we go too far, we are going to be working with two-way tables. These are going to be a very important tool for working with probability. So let's remember marginal distributions, marginal totals. We've got those right here, and hopefully you remember they're on the margins, which is why they're the marginal distributions. And then we've got the conditional distributions in the middle, kind of the body of our two-way table. And the bottom right is just the total number of observations, whatever that makes up the sample. So there you go. Let's see how we're going to kind of approach this in probability. So the marginal values are going to actually represent the probabilities of an event. So with this two-way table, the probability of liking snowmobiles, we're going to find that with the conditional. So if we look right here, not the conditional, I'm sorry, with the marginal distributions, the probability of liking snowmobiles, well, 105 people out of 160 like snowmobiles. So that's where we get this from. The probability of the complement of liking snowmobiles. Well, when there's only two options, that just means not liking it. If there were like 5 options, it would be everything besides liking snowmobiles. So that would be our 55 right here over 160. And that's where we get our probability from. All right, nothing earth-shattering. The conditional distributions become our conditional probabilities, and that's going to be a big part of this. Okay, so the probability of liking skateboards among people who like snowmobiles. So we have our condition, and we go back to chapter 2 or 3, I think it was, talking about all this stuff. Our conditional probabilities say among people who like snowmobiles. So here's my condition, who like snowmobiles. And among those people, what's the probability of someone liking skateboards? Well, it's 80 out of only this 105 population. So therefore, that's where that 80 out of 105 comes from. Okay, so far, so good, I hope. And we will kind of come back to the conditional stuff in a minute, but here is just something else that is useful to know. So if we talk about the probability of an event, like the probability of not liking skateboards, this kind of is redundant about what we just talked about. Probability of not liking skateboards is right here. Don't like skateboards, come down to the total. It's 35. Technically, it's 35 out of 160. All right, and we'll see in a second that there are situations where we can ignore the fraction, but hopefully it's clear in a minute what that means when we can ignore the denominator. The actual probability of A happening is 35 out of 160. Now the probability of A and B, this is not conditional. This is saying one person who both likes snowmobiles and likes skateboards. So the probability of a person being like that is going to be, in this case, 80 out of our total of 160. So what's the probability out of everyone that someone likes skateboards and snowmobiles? Well, 80 out of 160. All right. Nothing too fancy there, but it's important to realize that A and B typically falls in this top left corner. It depends on what our A and B are defined as. Okay. So now we can look at this. We're going to use our general addition rule looking at this two-way table. What's the probability that a person will like snowmobiles or will like skateboards? All right, and luckily we've got this to guide the way. We're not just randomly guessing or just throwing random stuff into an equation. So the probability of I'll put, let's see, snowmobiles. I'll put S in for snowmobiles, and it's not and, it's or skateboards is just going to be the probability, and when I say the snowmobile and skateboard, I mean liking it. So we could, if you want to change the notation there, you can. So the probability of A is the probability that someone likes snowmobiles. B is going to be the probability of liking skateboards, minus the probability of liking snowmobiles and skateboards. So here's where I can get that from. Probability of liking a snowmobile is 105 out of 160. Probability of liking a skateboard is 125 out of 160. And before we look at the last term right here, this is one of those things where if you didn't set it up right, if you didn't think through this clearly, and you were just using your addition rule, not the general addition rule, then all of a sudden you'd get a number 230 out of 160. And that should hopefully give you a really big alarm bells going off saying, I didn't do something right. There's no way this can be more than one. So I must have messed up somewhere along the way. So this is going to be, in this kind of situation, you can say, okay, what am I forgetting? Oh yeah, I need to subtract the overlap. Where it overlaps is right here. And 80 out of 160 like both. So I want to not double count those people. I'm going to subtract them away. We can keep it in fractions. You can turn this into decimals, your preference. So if I add those together, that's 230, and the numerator minus 80 is 150. Now, if you are, I imagine a lot of you are looking at this saying, well, I see a different way of approaching this. The only way that this fails is if someone doesn't like either, and you see that 10 right there. Well, that's the complement, right, to what we just found. So maybe you could approach it a different way. I don't want to confuse you, so I'm just sticking to the formula because that'll work no matter what kind of information they give you. But, you know, if you look at it and you just see up here, like, well, that means all of these groups like one or the other, so I can just add these three together. And that's going to give you, again, 150 out of 160. But using the formula is pretty straightforward. There's always a danger of giving you too many ways to approach a problem where all of a sudden, oh, I don't know how to approach this. I have about 5 ways of looking at it. So take it or leave it if that started to get kind of confusing. The formula is always a good guide to come back to. Okay. And we can do this one pretty quickly. It's the same idea. Probability that a person will not like snowmobiles or they will like skateboards. Will not like snowmobiles, that's 55 out of 160. I'm not going to write everything down. I'm just going to do the actual calculation. Or will like skateboards. We already found that as 125 is over 160. Of course, now we need to subtract the overlap. And the overlap are the people who both don't like snowmobiles and like skateboards. So that's going to be 45. I'm going to subtract 45 out of 160. When I add this up, that's going to be 135. Am I doing my math right? It's been a long week. Let's go with that. Seems good. 135 out of 160 is the probability. All right, so we started with the general addition rule because don't worry if you missed attendance. I got everyone's here today. You're good. So the reason we started with the general addition rule is because it's not that different and not that much more complicated than the regular addition rule. We just have to add this, factor in this one extra term. All right, is this going away? There it is. So now we're going to go back to conditional probability because we have special notation for that. And you might have come across this, certainly if you read the chapter you did, but you might have seen this in other places where you've got probability of A with the vertical line and then B. And what this means is the probability of A given B. It's just a shorthand for conditional probability. So I gave an example before. It's been a few slides, so you might have forgotten. But I phrased it as probability of liking skateboards among people who like snowmobiles. Well, I could have, in a little shorter way, written it this way. Probability like skateboards on condition or given that they like snowmobiles. So if that's the case, of course, we've already seen there's the condition being met. And then within that condition, it's 80. People like skateboards, so 80 out of 105. All right, just a repeat of what we saw, but now we're seeing it with notation. Okay. So we're going to find these probabilities. And anyone can write on the screen to show what these probabilities are. All right. Everyone happy with that? Okay. I hope so. That's correct. All right. I see 2 answers, but I can read them both. And both of you got that right. Very good. 125 out of 160. So I kind of created all these examples independently and didn't realize until I started going through the presentation that I keep on using the same things over and over again. Don't like snowmobiles, but you know, that's okay. We can still get the idea. Okay. So we got a few answers, and yeah, this is a conditional probability. So it's on the condition that someone likes, that these people like skateboards already, and how many of those people don't like snowmobiles. So it is going to be 45 out of the 125 who like skateboards. So 45 out of 125. And last one. Okay. Okay, there we go. So we got a couple of answers, and both of them are looking good. I think it was just misreading it that first time, Jacob, but you know what you're doing. And I did this for two reasons. First of all, it's just extra practice. So now the condition is not liking snowmobiles, and there's 55 people who don't like snowmobiles, and 45 of them do like skateboards, 45 out of 55. We're good there. The other reason I picked it is it's important to understand that flipping the condition and the event will change your probability almost every time. There can be exceptions, but flipping these two gives you a different probability. So don't assume, in fact, now you know that it's not true that flipping those will be equal. So in fact, there's, toward the end of the chapter, if you read, there's Bayes' theorem and Bayes' rule that kind of we can use to figure out one from the other. All right. And that is all good. Good work. Okay, so this is the other thing. This is kind of coming back to what we talked about earlier. Here's another way of thinking about conditional probability. The probability of A given B is equal to the probability of A and B over the probability of B. So let me go ahead and draw some stuff on here. All right. So the probability of of liking basketball or preferring basketball on the condition of being female, you know, you can see, and you could work that out. But we could also say it's just A and B, probability of A and B over B. Now this is technically the way I'd write this is the probability of A and B is 16 over 100. Because notice there's 100 total people. So 16 over 100 over the probability of B is 52 over 100. But notice that because I'm using the same denominator for both of them, I can kind of just think of it as 16 over 52 without worrying about anything else. Okay, so if you're trying to set up from that concept, not too complicated. Hopefully we're feeling good about that. Okay, and remember, just with all this stuff, it is a quick overview of a bunch of stuff in chapter 15. If you need to come back and rewatch, or just come in on, stay after class or come in on Monday with questions that you have, please be taking note of something of anything that might be confusing for you. So we needed to go through all this stuff with conditional probability because that gets us to our general multiplication rule. All right, and that was already on screen. Now you can see it there. The multiplication rule says that, and I'll write it in the same language, the probability of A and B equals the probability of A times the probability of B. But that's only if the events are independent. Here, it doesn't matter if they're independent, because now we're multiplying by B on condition of A, the probability of that. Okay, so we will have to make sure we're very careful about that. And I wanted to take a second just to talk about this comparison between the original multiplication rule and the general multiplication rule. All right, so here's our general multiplication rule. And we're going to look at a table with a two-way table with independent variables. And I'm telling you these are independent. We're going to talk on Monday more about reviewing more than anything else about how we know if they're independent or not. But for today, I'll just tell you these are independent. Being a senior versus a junior in this hypothetical data set doesn't give you any insight on whether the person is going to prefer in-person or remote learning. They're independent, those variables are. Okay, so let's kind of see what's going to happen in this diagram, or according to this calculation. Our general multiplication rule says that the probability of A times the probability of B on condition of A is going to equal to the probability of A and B. Now, the probability, we're going to say that A is being a senior. And it looks like we have an 80% probability of someone being a senior, 40 out of 50. Probability of B is going to be preferring in person. Well, here's the key part. The probability of B preferring in person is going to be 20 out of 50. So that's our 0.4. The probability of B on condition of A, so what's your preference on condition of being a senior? Well, 16 out of 40, if you do that, that's still 0.4. So whether we're using conditional probability or just the probability of event B, it doesn't make a difference. They're independent. So therefore, it doesn't matter if we use the general or the regular multiplication rule. But of course, most situations aren't set up this way. And if you need to come back and look over this example to try and wrap your head around it some more, of course, it's in the presentation. So we are going to use conditional probabilities, and we're going to kind of be looking at that. If you have a contingency table, it's actually pretty easy. What's the probability that someone will be a male who likes football? So here we go. I mean, I've already worked through this. We got the probability of being a male is 48 out of 100. So this is the probability of event A. 48 out of 100. The probability of liking football on the condition that that person is male is going to be your 20 out of 48. And when you multiply that together, essentially what you're doing is you're canceling out those two terms and you get your 20 out of 100. Now, could we have just read that from the 2A table? Yeah, 20 out of 100. But this shows kind of using the multiplication, the general multiplication rule, how we can arrive at that. Okay. So maybe what's going to be most helpful is to see some practice problems. And that's what I've got set up for you. How about that? And the hardest part of these types of problems is the very beginning. I think that's true of any stats problem. But if we start going through this, we've got some numbers given to us. Suppose the probability that a US resident has traveled to Canada is 0.18, to Mexico is 0.09, and to both countries is 0.04. What's the probability that an American chosen at random has? And then we need to find some probabilities. Now, the easiest way to solve this, in my mind, and I think the way that helps us wrap our head around it the best, is to create a two-way table. All right. Otherwise, we're trying to balance too many concepts and numbers in our mind all at once, and we're more liable to make a mistake. So I'm creating a two-way table. That's great. So what is going to be on my two-way table? I've got two categories, basically. Canada, have you been there or not? So Canada, yes and no. So the other variable here that I'm looking at is Mexico. Have you been there or not? And just on a brief aside, I have been to Canada and Mexico, and I've been equally far into both countries. Canada, I crossed into Canada just so I could see Niagara Falls, the Canadian Falls. So that's as far as I've been into Canada. And then Mexico, I was on the Rio Grande down at Big Bend National Park, and I went on the Mexican side of the river. So I have been into both countries equally far. All right, I know you were asking, and now you know. So anyways, Canada, we know that 18% of people have gone there, so yes, 0.18. This is my, remember the margins are where we put the probabilities for each individual variable, which means 82% of people haven't gone. This does have to add up to 100%. We're looking at relative frequencies here. Mexico, only 9% have gone, which means 91% of people have not. The other thing that they gave us, we couldn't fill out the rest of this table if they didn't also tell us that 4% of people have gone to both. And if I was answering this survey, I'd probably say I've been to neither country, not that I've been to both. So now remember something, one of the characteristics of two-way tables is that you have to, the frequencies have to add up across the rows and down the columns. So now it's just basic arithmetic. If I've got 9% on the first row and I've already got 4% accounted for, well, 9 minus 4 gives me 5% of people have are fall into that category. Going down the first column, I've got 4% and 18%, so the difference between those is going to be 0.14. And this last one's, if I did it right, it should satisfy both the column and the row. So looks like if I subtract 5% away, I'm going to get 0.77. I'll check it with the row. 14 plus 17% gives me 91. So we're all good. And now with doing that, our job is easy. So traveled to Canada, but not Mexico. Okay, I've been to Canada, so I'll do this in a different color. I've been to, what's going on? Okay, sorry. I've been to Canada, yes, but not Mexico. And it already tells me my probability right here, because these are relative frequencies. So I don't have to do any extra calculation. So 14% of people, so I'll just leave it as 0.14. Traveled to either Canada or Mexico. Okay, so now there are multiple ways of solving this, but I'm going to use the general addition rule, which says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, and these are all numbers I can pull from the two-way table. Probability of A is right here. I'll call going to Canada event A. So I've got 0.18. The probability of going to Mexico is 0.09. And the probability of going to both is right here where I've got yes for both of them. And that's minus 0.04, which gives me 0.23 is my final answer. Okay, so that's the hard part of this one, whether or not you think it's hard. Hopefully you find it easy. So now the thing we need to answer is, what's the probability that an American chosen at random has not traveled to either country? And we can get this one of two ways. We can either just look right here on the board and see the two-way table, see, okay, this 0.77, these are people who have not been to either. There's the answer. It's pretty simple that way. The other way we can think about it is that this has to be the complement of answer B. Because if you've been to Canada or Mexico, then you have traveled to one of them at least. So you don't fit that category for C. So 1 minus 0.23 gives me 0.77. And there you go. So any questions on this one? I don't think there's any more fun way of spending a Friday afternoon than watching someone do some probability. All right, do we want to do this one? Yeah, let's do this. Okay, we've already got a two-way table set up on this. It's just not complete. We're going to do the probability. I might skip around a little bit on this. We don't do every single problem. So we've got a two-way table comparing political party to opinion on death penalty. And anyways, we are missing our totals. So before we jump into the problems trying to figure out probabilities, it's gonna be important that we know the totals. And we know these have to add across the rows, down the columns. So if I go across, I'll just do the math real quick. You can do the same. Okay. And again, these are relative frequencies, which works to our benefit for these probability problems. So that's nice to have. Okay. The first one's pretty easy. Probability that a randomly chosen voter prefers the death penalty. Well, we don't care at all about political party. So the probability there, someone can write that on the screen. There it is, 0.62. All right. Probability that a Republican favors the death penalty. And I'm gonna let you guys try this one real quick. Okay, and that is it. Good job. And I bet there's at least one person, not sure how we got that number. Andrew, do you want to explain what you did?
Yeah. The total was 0.3, so I took 0.26, which is the Republicans in favor of the death penalty, and divided it by 0.3, and I got 0.86.
Okay. And this is one of these sneaky ones that is a conditional probability, which is the calculation that Andrew just explained, that you have to read it carefully to understand that. So it's what is the probability that someone, that we can think of it as this, what is the probability that someone favors the death penalty on condition that they're a Republican? Given that they're a Republican, what's the probability they favor the death penalty? So it's on this condition, 0.26 out of 0.30, and there's your 0.86. So hopefully that's making some sense now. And the last one, we'll just talk about it. We won't go through and solve it, but a voter who, okay, what's the probability that a voter who favors the death penalty is a Democrat? So what's the condition?
Those in favor.
There you go. So our condition is right here, and then is a Democrat. So you could do that calculation. And yeah, if you do this one and you want to solve it, make sure you get the answer right. It's just under 20%. So if you want to try that calculation and you get something just under 20%, you're good. So let's just look at the last problem. A candidate thinks she has a good chance of gaining the votes of anyone who is a Republican or in favor of the death penalty. What portion of voters is that? What do we got to use?
General addition rule.
Okay, there it is. And the key thing to be on the lookout for is the word or. If you see or, it's going to be addition rule of some kind. And here we know it's going to be the general addition rule. Okay, so what portion of the voters is that? So let's see here. We are going to do the probability of, well, what's one condition? Being Republican, plus the probability, what's the other? Being in favor of the death penalty. I can just put a plus to say in favor of, minus the probability of both of those being true. Republican and in favor of the death penalty. Okay, and we can just substitute those numbers in. So, I mean, I'll just do it just for completeness sake in case there's any doubt. 30% chance of being a Republican, 62% chance of being in favor of the death penalty, but subtract away those double counted people, which are Republicans in favor of the death penalty. That's 26%. And that is your calculation. All right. Hopefully feeling good about all that. I don't know if this seems easier, harder, about the same as what we've been looking at with probability so far. All right, sorry about that. This one, I just wanted to go over, this one won't take long, but let's just read it for a second. 20% of cars that are inspected have faulty pollution control systems. The cost of repairing a pollution control system exceeds $100 about 40% of the time. When a driver takes her car in for inspection, what is the probability that she will end up paying more than $100 to repair the pollution control system? Okay, so you can imagine we're going to be doing something with multiplication rule, because we have two things that need to be true. Okay, so the driver goes in for an inspection, and two events have to happen in sequence for her to get this particular outcome. She has to fail her pollution control system, so I'll just put F for fail it, and she has to exceed 100. So I'll just put 100, I don't know. You can label these variables whatever you like to help you. So fail and exceed $100 in the repair. So this is, it looks like we might not have enough information because we don't have a whole lot to work with, but I know that the probability of, I know what the probability of failure is. So that's going to times the probability of exceeding 100 on the condition that you fail. And the question is, do we have that conditional probability? Well, I think we do, that 40% of the time. So if I take this 20% of the time people fail, that's my first probability. The second one, the probability of exceeding 100 on the condition that you fail is 40%. Now, it doesn't quite say it that way, but here's just thinking through it logically. Who goes to get their pollution control system fixed? It's the people whose pollution control systems are faulty and need to be repaired. So we've met that condition. And so the 40% of people who are getting it repaired have met the condition of having it failed, if you follow my words and my logic there. So this 40% is a valid number to use right here. You don't go and repair something that's working perfectly unless you have weird reasons for doing so. So there you go. It's an 8% chance that when you go in to get your inspection, you're going to end up paying over $100 to repair your pollution control system. Okay, so that doesn't take a long time on that. It's just worth kind of looking at to realize that the conditional probability is embedded in the problem. Okay. Okay, yeah, there's a few more problems I wanted to look at. This one, there's something we're going to talk about more on Monday, and I'm kind of jumping into problems related to it without talking about it, but it's a pretty simple concept. So if you draw cards from a deck and you just keep drawing cards, the probabilities that you get for each subsequent card changes what that card might be, because now you've removed cards from the deck. It's not the same odds. You would say they're not independent at that point. So the odds are not independent. So that's kind of what's happening in this scenario. There's a big box of shirts. You can see the breakdown. It's a soccer team. They got 4 medium, 10 large, 6 extra large. That is a very husky soccer team. So anyways, you're going to be drawing t-shirts out of the box. Scenario is easy enough. And we're going to play it this way. We're going to say you're the first person to the box. You get to pull out the first shirts in every one of these scenarios. Otherwise, it's way too, who knows how to approach it. when you pull a shirt out, you don't put it back in. So that's the way we're playing this. We're going to find the probability of the first 2 shirts that we grab are the wrong size. We got mediums, larges, and extra large shirts, and we want mediums. So this is the probability of wrong size and wrong size given that we have a wrong size for the first one. So, all right. The probability of getting a wrong size, well, if there are only 4 that are correct size for us, then that means 16 out of the total. And we can count that up and realize there are 20 shirts. So 16 out of 20, but we've pulled a shirt out. Now we're going to reach in and grab a second shirt. What are the odds that I get a wrong size the next time around?
$16 out of 19.
Close.
Those.
Would it be 15 out of 19?
Yeah, 15 out of 19. Remember, when you pulled that first shirt out, it was wrong size. So now there's only 15 wrong shirts to pick from. No worries. So now we've got 15 out of 19. That would be the odds for the next time around. Now, this is one where it starts off maybe as a fraction, but I'm going to report this answer in decimal form. So I'll just do 16. Well, you know how to do that, so you can do that multiplication and division and all that fun stuff. All right, and that's what I got. You guys can't confirm that or correct that. Okay. Now, here is kind of something that we haven't talked about with the general multiplication rule. It's not in the standard formulation of it, but we could stretch the multiplication rule out as long as we want. It's not just 2 terms multiplied together. So here's what we could say, and we could say, I'm going to add some subscript here. So what I really am saying, I'm wrong on the first one, and then and my second event is that I'm wrong on the second one on the condition that I'm wrong on the first. Okay, so let's see this. The first medium shirt that we find is the third one we check. Okay, so that means on the first one, I'm wrong. And on the second one, I'm wrong on the condition that I was wrong on the first one. And the third one, I'm right. So I'll just put subscript 3 to show that it's the third trial, the third shirt I pull out. So if I could find all 3 of those probabilities, I could multiply all 3 of them together. So yeah, this multiplication rule can expand out depending on how many events are involved in the and. Luckily, I'm going to shorthand this. I've already done the calculation for this part of it. We already know that it's, for the first part is 0.632 probability that I fail the first 2 times. So now I just need to figure out, okay, so if it's that and, so multiplied by the probability of getting the shirt correct on the third trial, what is the probability of the third time around getting the correct shirt?
4 out of 18.
4 out of 18. There's still those 4 correct shirts right here, but now there's only 18 to pick from. There it is. Now we can do that multiplication. And depending on if you truncated your answer you know, and re-put it in the calculator, you might be a little bit different from me. I used the full decimal, but whatever the case, you should be in that ballpark. Okay. So assuming everyone's good, and if, again, any questions that you are lingering, just stick around afterwards, we can go over it. But the first 4 shirts we pick are all extra large. We pick 4 shirts. Not only are they wrong size, but they're all extra large. So we can't use any of our previous calculations. We're going to have to start over. So I want the probability of extra large on the first and extra large on the second, given that I got extra large on the first, and extra large on the third, given that I got extra large on the first and second. And you can see where this is going. Extra large on the fourth, given that I got extra large on the first, second, and third. So again, each one of these terms is just going to be another probability that I multiply together. There are 6 extra large shirts to begin with. So tell me my probabilities in order. So for the first shirt I pull, what's the probability?
6 divided by 20.
There it is. All right, I did that. The next shirt, what's the probability?
5 divided by 19.
Yep. The next one.
4 divided by 18.
Okay. We can see the trend happening here. And what's the last one?
3 divided by 17.
There it is. All right. That can be multiplied out. And I know it can take a little time to put these numbers in the calculator. If that's taking a little bit of time, no worries. And I'll just kind of start talking about the next problem. I know I'm going a little fast. I apologize if I'm rushing you through something. But as long as you understand the process, you should be able to kind of punch those numbers in the calculator, come up with that right there. Again, correct me if I made a mistake. I think that's correct. All right. So what we're going to do now is look at this other case. And this goes back to our bell work. So this is one of those at least one phrases, which if we know what to expect with that, it doesn't make it significantly harder. Okay, so I'm gonna erase everything that I've got here. And I wanna think about it as the probability that I don't get a medium 4 times in a row. So I'll put the complement of getting a medium and the complement of getting a medium. I know I should maybe do some subscript because it's, but that's gonna, I'll just find whatever. All right, I'm not gonna do it the whole way through, but you know, another and another. So it's all conditional probability on condition that we didn't get it the first time, second time, third time, and fourth time. We don't want to get a medium any of these 4 times. And then that means we failed. So the complement of that is the probability that we succeed. All right. So now let's figure out our failure probability. What's the probability that we fail with the first shirt, getting a medium?
16 out of 20.
There it is. For the second shirt, what's the probability that we fail?
15 out of 19.
Uh-huh. All right. So this is going to sound very familiar. Third try, what's the probability?
14 out of 18.
We're getting it. Good job. And the last one is going to be
13 out of 17.
13 out of 17. Of course, when we get this, we want the complement of it, but we'll do the big calculation first. All right. So this is another one I wanted to look at. In some ways should be a little bit easier. Part of it we're going to skip for right now. But this is another case where, just like the first problem we started going through, we're going to want to create a two-way table. We've got some percentages. We can put those in. And we've got a couple of variables we're looking at. We are looking at American workers, 56% of whom have workplace retirement plan, 68% of whom have health insurance, and 49% of whom have both benefits. We're going to select a worker at random, and what's the probability of X, Y, Z? Okay. So we can figure this out. We've got two variables. One of them is, do you have a retirement plan? I'm just going to put R for retirement, yes or no. And then the other is health insurance. I'll put H. Do you have it? Yes or no. So according to this survey, 56% do have a workplace retirement plan. That's 0.56, which means 0.44 do not. 68% have health insurance, 0.68 for yes, 0.32 for no. And then the last number that we need is this 0.49, have both benefits. So now what I want you guys to do is fill in the rest of that table. I know it's kind of small, so it might be hard without a stylus, but see if you can fill in the rest of that table with the other numbers. Okay, so we've got it. I know this is a 0.25. I'm just going to draw the point very clearly. So we've got our relative frequency two-way table. And again, if it's relative frequency, that makes our life so much easier. So let's go ahead and look at this. The probability that this random employee has neither employer-sponsored health insurance nor a retirement plan. Hey, that's easy with the two-way table. What's that answer? You can just circle it on there if you want or write it out. There it is, 0.25. Okay. The probability that he has health insurance if he has a retirement plan. And again, I'll pause and I'll let you guys try and answer that one. We've seen something like that already. All right, so we can see the 0.875. So, and I think I know where the other answer came from. So real quick, can you put that up there? If you don't want to, you don't have to, but do you want to explain what you did to get your 0.875?
I divided the 0.49 from yes, both yeses, by 0.56, which is yes for retirement.
Got it. Okay. So here's the condition is that yes, it's retirement plan, and the event is having health insurance. So the other answer we saw, it was the right idea, just accidentally used the condition of having a health insurance, and the event was having a retirement plan. So just mixing those two, but it's still good to see that just flipping your condition and event will change your answer. Okay, I'm going to skip part C. And the last one, are these two benefits mutually exclusive? This is the easiest kind of question that we have when we have a two-way table. Because remember, if these events are mutually exclusive, one of the definitions is that the probability of A and B for mutually exclusive events is 0. So all we have to do is look at this top left corner. If that's not 0, they're not mutually exclusive. So 0.49, it's not 0, they're not mutually exclusive. And what we can say, it says explain, no, they're not, because, and I'm not actually going to write it all out, because ... you can have a health insurance plan and a retirement plan at the same time. So that's why they're not mutually exclusive. But really important to see that. We'll talk more about independence and everything else on Monday, which is going to be more review than anything else. So we'll skip this problem for now. There's your homework. Some of these are going to be related to independence. You can skip those. And so, again, I mean, I say this a bunch, but some of these problems are going to be redundant. You're going to do one, you're going to look at the next day. That's just doing the same calculation again. So if you get the idea, just do it until you feel like you really understand it. And of course, turn in the one problem that I expect. So let me know if you have any questions. You can stick around, come in on Monday with some questions that you have. And besides that, have a wonderful weekend, and I'll see you on Monday.